And welcome back to our water pollution unit. In this podcast, we're going to take a look at how water pollution works in streams and lakes. Now, the major difference is that because streams and rivers are in motion, they actually can clean themselves if we don't overload them or reduce their flows. On the other hand, when you're dealing with adding excessive nutrients to lakes, that becomes a little bit bigger issue. And so in that case, prevention is much more effective and less costly than trying to clean it up. Now, when you're looking at streams, there's a couple things that you got to look at. First of all, anytime you add pollutants to water, there is a diluting effect. Now, there was an old attitude that said that dilution is the solution to pollution. And while there is an element of truth to that, that's not actually the right attitude to have. It's a slight benefit, but over time, those pollutants oftentimes will add up, and now you have a real issue. But in the short term, there is a dilution effect to it. The other issue is that if you're dealing with biodegradable waste, they can be chewed up by bacteria and gotten rid of, but that does deplete the oxygen that we've talked about, and so we want to take a look at how that looks in rivers. All right, so if you take a look at this graph, this depicts the oxygen sag curve. And if you look up here, kind of in where this pipe is, that's going to be your point source pollution. That's going to be putting some biodegradable pollutant. This doesn't work when you're talking about mercury and lead and those types of things, but when you're talking about some type of a cellulose base, anything that's going to be biodegradable. So we're going to start our story on the left here, where the dissolved oxygen levels are going to be around 8 parts per million. And in high oxygen level waters, you're going to have the more specific species, those that have a very narrow range of tolerance, such as trout. Trout need cool, high oxygen waters, as does their food sources like mayflies and stoneflies and such. And the biochemical oxygen demand is relatively low. There's nothing necessarily in the water that requires that bacteria are going to be using for food in large quantities. But once this organic, biodegradable point source pollution is introduced, now your biological oxygen demand is relatively high, and so the bacteria start chewing on that, decomposing it using oxygen and aerobic respiration, so that the oxygen level is going to decrease through the decomposition zone. Now, while the oxygen is decreasing, now those oxygen tolerant fish, those that can go with low oxygen, such as carp, you're going to find much more of those fish in those particular areas. You're not going to find your trout and your bass in those areas because there's not enough oxygen for them. Eventually, the oxygen goes so low, we now are calling it a septic zone, an area of low to no oxygen. And here you're not going to have any fish. You're going to have bacteria that are going to undergo aerobic respiration, fungi, those types of things. But nothing in the order of larger, higher order organisms. But what does happen, because the river is moving and because it can mix, you have oxygen that's introduced from the atmosphere to the surface, and through wave action, as it crashes over rocks, etc., it's going to re-oxygenate itself. The food source has now been chewed up, so now the bacteria, because the bacteria doesn't have any food sources, their population declines, and the oxygen returns back to normal levels, and the biochemical oxygen demand is now gone. And so now you basically have a restoration of the river. So that's your prototypical oxygen sag curve when you have biodegradable pollutants added to a river. Now, things that are point source pollutions, as we were just pointing out, those are actually all federally regulated, and they're regulated through a major piece of legislation, the Clean Water Act of 1972. It's been amended several times since then, but the primary legislation that finally had some teeth, it started back in the 1940s with the Federal Pollution Control Act of 1948, but it wasn't until the 1970s that it actually got some teeth. And what it does is it controls discharge from point sources into navigable waters, or waters of the United States. And that's kind of an odd way of describing it, but that's very important. All environmental law is based on the Commerce Clause in the Constitution. Of course, all laws have to be constitutional. And so what actually allows the feds to regulate the environment is the idea, in this case, that it does impact commerce. Because commerce takes place on waters, you have shipping up and down of rivers, etc. Because of that, the federal government has the authority to regulate anything that impacts interstate commerce. And so that's where this term navigable waters came from, in waters of the United States. Now, through several Supreme Court rulings, a couple of them occurring here in Michigan, navigable waters, or the idea of navigable waters, is much broader than what you might think. You might think that the navigable waters only really refers to anything that you can get a ship or a boat into, and that's really not the case. The Supreme Court has actually ruled that navigable waters is a much broader definition than that, and so essentially the feds can regulate any type of point source water discharge, and they do it through a permitting system using this National Pollutant Discharge Elimination system. So let's take a look at what that looks like. I'm just going to go to the web page for that. So this is through the EPA, the Environmental Protection Agency, and I'm not going to go through all of this, but essentially what happens is we are looking at regulating the discharge in major areas, actually any discharge, but here's some of the major program areas. Animal feeding operations, again, agriculture is the largest industry. Industrial wastewater, municipal wastewater, that's going to be talking about how cities clean wastewater and then discharge it back into rivers and lakes, etc. Pesticides, stormwater. We'll be talking about municipal wastewaters and stormwater later on in the course. Vessel discharges. We're talking about both in the Great Lakes regions, up and down major rivers, along the shorelines of the United States, etc. All of that is regulated through the Clean Water Act, and is through a permitting system. All right, so that's one piece of legislation you're going to definitely need to know for this unit. Now, we have had some success stories cleaning up these highly polluted rivers, and one of them is pretty darn close to us here. Cuyahoga River, which actually flows through Cleveland, actually caught on fire several times throughout the 1960s. And the short story is that there were so many oils and gasolines and organic compounds that floated down the river. They're flammable. There was so much of it that a spark ignited the river. So you imagine the sight of water flowing that's actually on fire. And that really caught the conscience of Americans. That has since been obviously cleaned up, and the Cuyahoga River has restored by and large. Another major river that flows now through London, this is the River Thames, was considered biologically dead in the 1950s. It was essentially an open sewer for London. Now remember, London was the first city to clear 1 million people, and that occurred back around 1800. And so where were they going with all that sewage? They were just dumping it right in the river. And throughout the 1800s, tens of thousands of people died for a variety of different reasons. Cholera in particular, which is a waterborne disease and is highly, highly contagious or transferable. The River Thames was a sewer, and since then has been cleaned up. We mentioned the toxic algal blooms that would take place in Lake Erie. Well, not all of them are actually toxic, but back in 2014, the short story is that one of the toxic algal blooms, we actually detected what's called microcystin. Microcystin is a toxin that's released by certain types of blue-green algae, and it is toxic for human consumption. And when they found that in municipal waters, they had to shut down the water of Toledo. And so for 3 days in 2014, 400,000 people were without water. They were flowing into Michigan to try to get bottled water, etc. It was a big deal. You got to think about all those people that are in hospitals that need water, etc. That went without water or had to find other sources of water. So municipal waters and algae is a very, very big deal. Now, half of the world's major rivers are in fact polluted, and it's coming from untreated sewage and industrial waste. And when you're talking about the lesser developed countries, they don't have the infrastructure currently and the legislation and the enforcement to prevent this from happening. And so you have a lot of pollution. This is an image from China, just upstream from the Three Gorges Dam. China, as it turns out, they have a lot of pollution problems that they're working to solve. Now, when you're talking about lakes are going to be more challenging than rivers, because rivers, again, can't, because of the flow of the water, can reintroduce oxygen. But with the stratified layers and deeper lakes, you get very little vertical mixing, and you get very little water flow. So it can take about 100 years to change the water in the lake, and the toxins often are left behind. And if they are going to be fat soluble, they are subject to bioaccumulation and biomagnification up the food chains. Now, there's a couple of phenomena you should be already familiar with. Eutrophication. You have eutrophied lakes and oligotrophic lakes. Now, eutrophication can be and is a natural phenomenon where you have nitrates and phosphates that are part of the natural nitrogen and phosphorus cycles that will make their way into shallow lakes, slow-moving streams, and it actually makes them quite productive. You have high net primary productivity rates with those. Versus oligotrophic lakes, these are typically going to be glacial lakes, kettle lakes. There's not a lot of nutrients in them. They're very clear. They tend to be cold. Right, and you'll see an oligotrophic lake on the lower right, where your eutrophic lake is going to be in the upper left. It doesn't necessarily mean that the water in the eutrophic lake is bad, and the water in the oligotrophic lake is good. Clear does not mean good, and having some algae doesn't necessarily mean bad. You'd actually have to do a water analysis of that. But those are just two different types of lakes. Where you run into issues is when you have what's called cultural eutrophication. And that's where humans introduce extra nitrates and phosphates from, again, farms, feedlots, fertilizers, fertilizing lawns, mining situations, sewage plants, and that's where you get massive algal blooms above and beyond what normally should be there, and that's what leads to the dead zones that we've already talked about extensively. So really what you need to do is remove nitrates and phosphates from the products that we use. And then in terms of cleanup, you want to you can mechanically remove weeds and whatnot, and then you can also use moderate amounts of herbicides and algicides that help control those plants and algae in those lakes. You can also help reintroduce air by using fountains and bubblers to help reintroduce oxygen into those systems. And again, this is a cultural eutrophication situation in China. We've already mentioned extensively the amount of nitrates that are flowing into the Gulf of Mexico. It's nearly tripled since 1950, which has caused these algae problems. But then you also have the flood controls along the Mississippi River, which is a good thing in terms of protecting property and people, but it also increases the flow of the Mississippi River, which will only increase sediment pollution moving downstream. Now, what we've done here in the Great Lakes region, because of eutrophication issues of Lake Erie was considered dead in the 1970s, early 1970s. So the United States and Canada came up with a Great Lakes Water Quality Agreement, which did many things. And in particular, the things that we want to make sure we understand is it cut down on industrial waste being dumped into the Great Lakes watershed. It also, we were among the first communities to ban phosphates in a lot of household products, including detergents, and also it's harder to find phosphates in fertilizers, so we're trying to get that and reduce the amount that gets into our rivers. But we still have plenty of problems with sewage issues, particularly when treatment plants are inundated with stormwater. We still have plenty of non-point runoffs from farm fields, atmospheric depositions from power plants, particularly with mercury. You also have atmospheric deposition of pesticides, depending on how they're sprayed, getting into our waterways. Urban sprawl and runoff causes a lot of organics and compounds to run off into our waterways. We deal with biological pollutions, including zebra mussels. Asian carp is a concern, etc. So in class we'll talk a little more about the Toledo water crisis, and then also the Flint water crisis that occurred, and we'll get into the details of why those are both major issues that you should be aware of in this particular region. In the next PowerPoint, or the next podcast, we're going to talk about how pollution impacts groundwater. Stay tuned.